Alright, so we stopped at the end of the other video and we're kind of dovetailing into the next video where we're using the mean value theorem. This is all again the mean value theorem, but instead of using the original function, we used it with the second derivative and we get this result. And what we're trying to do here is prove the Lagrange error bound. So we want to get f of x involved in here somehow. And to do that, we have to take the antiderivative of everything with respect to x. Okay. And when I do that, I'm going to do this quite quick. On the left side, I get the third derivative of f at c, because that's a constant, times x minus a quantity squared over 2, so that's the antiderivative of this part, is equal to the antiderivative of the second derivative, so that's just f prime, minus f double prime of a times x, because f double prime of a is a constant, plus a constant, so k. Now to solve for k, we set x equal to a to solve for k. And when I do that, if I put a in here for x, this whole thing goes away and I end up with 0. And on the right side, I get f prime of a minus f double prime of a times a plus big K. Rearranging, I get that k, whoops. So just taking all of this and moving it to the other side, I get that f double prime of a times a minus f prime of a is equal to the constant that comes from the antiderivative. And then I'm going to take this result here and just put it back into that original function. So I get the third derivative at c, x minus a squared all over 2 is equal to f prime of x minus f double prime of a times x plus this mess, f double prime of a times a minus f prime of a. Whew. But just as before, I'm going to be able to do a little bit of factoring here. So I'm going to take f prime of x minus, just factoring a negative 1 out of everything. So I get a positive f double prime of ax, a negative f double prime of a times a, plus f prime of a. And then I can go a step further and we get f prime of x minus, and again, not surprisingly, just like before, we could factor this as well. We could factor f double prime of a out of there, and I get x minus a plus f prime of a. Okay. And all of this is equal to the third derivative at some point c of x minus a squared all over 2. Now you can kind of see where I'm going with this. We want to get f of x in here somehow because we want to show the difference between f of x and its kth degree polynomial. So we take the antiderivative yet one more time. So the antiderivative of what's on the left here is the third derivative at c, because that's a constant, times x minus a to the third power. I still get this 2 here. And then in order to adjust for this third power, I have to multiply by a third. Okay? So over here, I get the antiderivative of f prime, which is just f, minus some stuff in here, f double prime of a times x minus a squared all over 2. Okay, this should look very familiar. Plus f prime of a times x, okay, plus some constant. And I already used k before, so I'll use k2 now. Alrighty. So now to solve for k2, to find out what the constant is for k2, I'm going to set x equal to a. In other words, I'm substituting a into x. All of this here goes away. I get 0 for that. I get f of a minus, I get 0 for all of this, and this is going to give me f prime of a times a minus k2, because I'm distributing this negative sign here. So move k2 to the other side, and I get that k2 is in fact equal to f of a minus f prime of a times a. Then we're going to take this result and just substitute it into here. And let's see what happens, and it should be very familiar. Okay, so taking this whole equation up here, f, the third derivative at c of x minus a to the third power over 2 times 3 is equal to f of x minus, what's in here? F double prime of a times x minus a squared all over 2 plus f prime of a at x plus k2, which is f of a minus f prime of a times a. All of that in parentheses. Now I can factor out these. If you look at these two here, they have a f prime of a in common. So this will become f prime of a times x minus a. I still get this f of a right there. And over here I get f double prime of a times x minus a squared all over 2. This is x minus a to the third all over. And if you look at here, this is really 1 times 2 times 3, which is nothing more than 3 factorial. Okay. And, oh, I forgot a plus here. Okay. All right, so let's review here. This is f of x, this is the Taylor polynomial. Okay, or at least it can be replaced by the Taylor polynomial since we're using the Taylor polynomial, or the Taylor series, to express f of x. This right here is the Taylor polynomial up to the second degree, so this is another way of saying t2 of x. And what do we have over here? This is the Lagrange error bound. For the Taylor polynomial of degree 2. Okay? So you see, this all starts out with the mean value theorem that we just apply over and over and over again. And if we wanted to find what is the Lagrange error bound for a Taylor polynomial of degree 50, we would just do this pretty repetitively, and eventually we would get to the same thing. So there you have it. Between this video and the last, you have kind of a proof. Now there are much more rigorous ways of doing this, but hopefully this helps you see where this idea at least comes from, so that it doesn't just seem like it's some magical thing or some weird type of witchcraft that this comes out of. And again, if you look at the previous examples, this Lagrange error bound is quite powerful because it allows us to take an estimate and say how close it is possibly to the correct answer, okay? Or put an upper bound to say that it's no worse than a certain distance from the actual answer. As always, if you need help, please ask for it. Thank you for watching, and have a wonderful day.